additional tidbits about the SAFRA Center. As I said, we are 27 research groups now. 10 of them were recruited over the last 10 years of the center. So we've been really growing nicely. And 12 of the alumni, the students who took part, who were in the center as students, are already in faculty positions, both in Israel, in 4 different universities, and abroad. So I hope that in 5 or 10 years we will be able to tell equally or even more impressive numbers. So let's move to the real program, and it's a great pleasure for me to introduce Professor Mike Waterman, who is the first speaker. Professor Waterman made seminal contributions to bioinformatics. Everyone in the field knows the Smith-Waterman algorithm, which is the basis for sequence comparison, that is the working horse of computational biology, or the Lander-Waterman model for evaluating mapping, which is the basis for every planning of sequencing a new genome. Professor Waterman had numerous other contributions to haplotyping, to the introduction of graph theoretic methods to sequence assembly, which is now essential because of the deep sequencing techniques, and to many other projects. And in addition to all this, he's been one of the founders of bioinformatics as a community in terms of publishing the first textbook in the field, founding the RECOM conference, and the first journal in the field, JCB. Professor Waterman won many awards. I'll just mention very few. The Gardner Foundation Award, and his honorary doctorate at Tel Aviv University from several years ago. And he's a member of the Academy of Science in the US, France, and China. Please welcome Professor Waterman.
Thank you, Ron. My directions for this talk was, Ron told me to prepare a talk for 45, 50 minutes. I did that, and then recently I revisited my undergraduate university, and it brought up a number of sort of quasi-historical things. And so our Dan David Prize there's 3 levels: retrieving the past, the information revolution, and bioinformatics. So I'm actually going to talk about my past for a little while. This is unconventional, I realize, but I promised Cyrus's wife, in fact, that she would understand the first 15 minutes of my talk. And I still think it's true. Let's see, I'm not managing to move. Control L, okay. It's not exactly moving. It's still fantastic. Okay. I'll move this over. So I'm going to start with a picture of the schoolhouse my father went to, and this was in a little bit past the mid-1920s. This was before the Depression hit America, and there it is. He's one of those. I don't know which one he is. This was his schoolhouse. He was born about 1 kilometer in one direction from this building and was raised in a house about 1 kilometer in the other direction. And eventually he was to buy this property. He was not a man with a lot of imagination of life, and he spent his entire life in this little place. And the next slide, I sort of want to give two. We raised livestock and open country, and the winters were really hard. The animals were out there trying to get enough grass. And if you can look carefully at this sheep, she has a lot of wool. She successfully survived the winter. She has her lamb, but you can see she's very bony underneath that heavy coating of wool. But the reason this slide is there is at the top of the picture is this barn. And we called that the Schoolhouse barn. The barn that my father went to school in was dragged down the hill a little bit. Wings were built off the side, and I shoveled hay out of that barn to cattle in the wintertime. The winters were long and cold and miserable, but just to show you it wasn't all bad, here's a picture of me as a boy. The school I went to was not quite as grim as my father's school, but as soon as I learned to read, there was no electricity here, there was a lot of labor, and I learned to read and I could escape in books, but I couldn't get my hands on enough books. The school hardly had any. My family didn't have books. I was dying for books. So this is the information connection. And in fact, when which is the next slide? Yeah, this is a Barbara Tuchman quote. Without books, history is silent, literature dumb, science crippled, thought and speculation at a standstill. I discovered science existed when I was in the 7th grade, and I couldn't get my hands on a book that explained anything, just sort of trivial stuff. But the idea that there was a way to understand how the world worked just set my brain on fire, but I couldn't get my hands on it. When I went to Oregon State to college, I had, as I say here, the naive idea that, from my experience, that there were so few books in the world that I would basically read all the ones I wanted to, and then what was I going to do? And then on campus, I found the library. And it was an incredible shock. I didn't know what to do with these rooms, with all these books. How could I find what I wanted to find? So it was exactly the opposite problem. Flip the world. And I still miss libraries. This was the library at Oregon State, Kidder Hall. So I was there 4 years and then did a master's for 2 years. And about that time, a new library was constructed. All the books were taken out of Kidder Hall, and they moved the math department into Kidder Hall, where it still exists. And I wrote a master's thesis in a room in this building, which eventually was actually published in Annals of Statistics. So here we are. I've spent my life collecting books. My house is full of books, bought lots of books. And then, and I love rooms full of books. There were, at the ceremony last night, if you were there were these marvelous pictures of libraries. But what's happened today? The world has flipped again on me. We have Kindle, Google, Wikipedia, etc. It's just really, really changed. And that, I think, is the theme that I want to go through for the scientific part of this talk. So I use the word big data in the title because I think it's such a buzzword. But the easiest way to talk about what's happening in biology, I think, is just the onslaught of data from next-generation sequencing, which is the root of this information. So here's 3 bioinformatics topics: sequence assembly, genome coverage, sequence comparison, that we had fairly adequately solved, and then we got these machines that were just pouring out sequencing data, and we had to find new solutions. And I think, the wonderful thing about this is that human beings seem to come up with some way around impossible difficulties, which is just marvelous to watch. So, we haven't been reading DNA genomes very long. 1995 is the first free living organism that was sequenced. And we go through to the human genome sequence 2000, 2001, where there were heroic efforts by David Hausler and Jim Kant at Santa Cruz to assemble the public data, and an incredible effort by Gene Myers at Celera to do that assembly. The problem, I think, as most of you know, you get reads randomly located on the genome on one strand or the other. You don't know which. The reads have some errors in them, and you have to take these little pieces and overlap them and stitch them together. The outline for this, and repeats are an incredible problem, which I'm going to talk about. But the outline, and I always think that Roger Staden at MRC came up with the first assembly program for the beginning of modern DNA sequencing, and I think the assemblers through the Human Genome Project were very sophisticated, souped-up versions of Roger Staden's idea, and it's what any of us would do, I think. You have a newspaper article that's Xeroxed many times, cut up into little pieces and mixed together, and you reach in and pull out, and you're trying to reconstruct the article. So if eventually you get two pieces that overlap quite a bit, you believe that, scotch tape them together, and go on. That's Roger Staden's approach. The approach called Overlap Layout Consensus. And the first step is you look at all the possible ways to overlap the reads. Then you look at groups of overlapped reads that are consistent with one another to do clumps of overlaps, or so-called contigs. And then finally, you take these overlaps, which aren't all identical letters in columns, and try to infer the underlying sequence. The first step is actually the easiest of these three, in my opinion. They're all really difficult. In the Celera project, there were almost 27 million reads, and if you just took a naive approach to the procedure I just skimmed through, there are 7 times 10 to the 14th pairs of reads, and if you did a sort of the dynamic programming comparison, the product of the lengths are the computation time for doing one pair. So if you just did this naively as I outlined, it would be a huge computational problem. Now, David and Jim and Gene were, of course, did all kinds of shortcuts on this, but that's the idea. And then, and I was around Celera during this time, and there were a couple of big rooms that were going to be the sequencing rooms. And they were going to be full of people and sequencing machines. And when I got there, there were a couple of these machines, these ABI machines, on one wall, no people, they were just silently working. And I thought this was the most modern thing I had ever seen in my life, and now it looks like my father's schoolhouse. So, for sure, assembly up to 2001 was challenging. Very, very smart people and lots of ingenuity went into it. And then we came to next generation sequencing technology, which I'll just hint here. Illumina, Solexa is a standard brand. There's all kinds of developments going on here for sure. And this slide, many of you have probably seen, but I show it in every talk. The cost for a megabase of DNA sequence, 2001 to 2012. The Moore's law is halving every year, I guess, year and a half. And so that's the top line, and the actual cost are the graph that dives. So it goes from $8,000 in 2001 to 8 cents in 2012. And imagine what that cost back say in 1985, when it was something like $17 a base pair. So he went from 17 million to 8 cents. And there's a factor of 10 for sure to come in here. So this is going to be incredibly available. So what happens to assembly? The old methods just didn't work anymore. And as Ron mentioned, I was lucky enough to stumble onto this Eulerian graph G-Broin approach. And I don't go into any details, but you take the reads and you do something very unintuitive. You look at all of the overlapping, say, 25-letter words in this read. You merge the identical words from the different reads, and you make those words the edges of a graph, which makes it a Eulerian path. Now, if you did sort of the obvious things, if the reads were of length 3, and you made the reads the vertices of the graph, you're trying to find a path that visits all the vertices. It's a Hamiltonian path problem, computationally challenging, but Euler was really smart. He made these guys the triplets. For example, the first AT to TG, the edge is ATG. So it's the T's are the overlap. And you're trying to find a path that visits all the edges. And for here, this is you don't have to be smart to do this kind of. Now, of course, with real genome sequences, stuff is it's really challenging. But I was lucky enough to stumble onto this. Pavel Pevsner had worked on Eulerian graphs for sequencing by hybridization. So this was a nice next step. And a postdoc and I published this in 1995, and almost no one paid any attention to it then. Dropped out of go the right direction. So the advantage of this, if you're lucky at linear time, you're not doing any alignment, you're not doing any layout, you're not doing any consensus, and insertion deletions are just as hard or easy as mismatches, which is not the case in the methods that I used to use. One of the things that I know Gene Myers wrote papers about was the orientation. In these reads, you don't know which strand. Are you trying to assemble, say, the top strand or the reverse complement? And getting that orientation significant, because there are 2 orientations for 27 million reads, for God's sakes. That's a problem. Ramana and I realized we just duplicated the reads. We just put in the read and it's reverse complemented. It would only double our computation time and we wouldn't have to think. That made us very happy. The difficulty of all this is that there are erroneous edges, the graph is tangled, and the storage requirements are just huge. And my idea was that for each of the K-words, we would keep track of what fragment it came from and where it was in the fragment. Are you giving me a time signal, Ron? No, okay. I'm trying to speed through this. So this would just, you couldn't continue to burden the storage requirements here. So there are all kinds, so people have then come on to this new solution and added really smart things about storage. For one thing, the forward, backward, this reverse complement thing, they store those guys together. They keep the graph as a distributed hash table. They forget the multiplicity of edges, try to attain a few words to summarize the K-words to reduce the storage requirements. So there's all kinds of stuff going on here now. Again, response to this huge data thing. So genome coverage, and Ron mentioned genome coverage, which Eric Lander and I were sort of lucky enough to write a paper about. And they were formulas for how many clumps of reads would you get, how long would they be, what kind of progress were you making. And you could even get the fraction of the genome covered. Paired ends caused us a lot of problems theoretically. People have struggled with, there's never been a complete satisfactory solution there. But They were really useful then, but I don't think these formulas are very useful now. Illumina, at least until recently, recommended Eric's and my formulas, but in fact, they're really not so great. And what's going on is huge coverage. An average depth of 50 and even 100 is possible, and the libraries are seldom. You don't have Hamilton Smith making very carefully a library with uniform representation. So you've got to have something else. And Andrew Smith, amazingly, at my place, pioneered quite a different approach. So here's the picture of what's going on. You have the molecules are amplified by PCR, and then that's mapped to a reference genome. And in this picture, we've got 4 or 5 of the molecules from the left is mapped to this place, and maybe only 1 from the right. And you can have libraries. The libraries that Eric and I wrote our paper about are the ones in the top, where all of the fragments got uniformly amplified. But they're so-called lower complexity libraries where certain pieces get amplified a lot and others are hardly amplified at all. And how the heck do you estimate genome coverage for stuff like that? So Andrew's approach, which is kind of has some surprising elements. His recommendation is to do a test run, check out the number of unique reads that you get out, and here the one on the left, after 1 million reads, if that's orange, the orange one is high, the blue one is not as high as whatever that is on the right, purple maybe. But if you did 50 million reads, the blue would be a lot better than the purple. How in the heck could you tell that from 1 million reads? The answer is you turn to the humanities. But this traces back to something R.A. Fisher knew about this. I.J. Good wrote papers about this. Capture-recapture statistics. So if you went out and captured butterflies and looked at how many species you had, how would you justify to your funding agent going out and catching another 1,000 butterflies? How many new species could you promise them? That's a pretty hard question. An analogous question that Brad Efron wrote a wonderful paper about is how many words did Shakespeare know? So we've got Shakespeare's plays, and we've got his word usage. We know how many words he used exactly once. We know how many words he used twice. We know how many words he used 1,100 times. But what we don't know is how many words he used 0 times. And that's the problem. That's the estimation problem. And of course, you could do this microbial species, genetic variants, whatever. And this is a picture, for example, of the how many words 1 time, 2 times, and so on. And the N0 is what we're after. And I didn't do any more detail about this. I really recommend his papers. This is really cool stuff. Empirical Bayes is the approach. And I guess I could say one thing else about that. Whereas lots of work done in this area, but the amount of data Andrew had required him to do some really novel new things. And of course, that's my theme here. Sequence comparison, hear a lot about my work in sequence comparison. It started as soon as people had sequences, and then we moved to the local alignment problem. And here, I emphasize both computer science algorithms and statistics. What's the p-value associated with your result are both essential. Traditional alignment. How am I doing for time, Ron? Okay, great. So in traditional alignment, what are we doing and why are we doing it? We're looking for the ancestral word of what and why. So here it would say WH, and either an A was added or in one word or erased from another word. and T and Y had some ancestral letter that they both evolved from. So we put scores on the letter against letter, and we put scores on the eraser part, and we're trying to get the maximum of all those. And there's a nice quadratic algorithm for that. For local alignment, essentially, the trick is just that we're looking for the two intervals that have the maximal score. And my algorithm, Temple-Smith, is quadratic time. And that's what, when you run BLAST, that's what BLAST wants to do. And it's an incredibly sophisticated heuristic for this algorithm. Well, we can't keep on doing that. So there's a very naive sequence comparison method that we worked on called D2. And essentially, you just look at the counts of each k-letter word, pick a k equal 4, say, and you look at the counts of the 4-letter words in one sequence, the counts of the 4-letter words in the other sequence, and you just multiply, for example, if W was all T's, you would look at all T's in the A sequence times the number of all T's in the B sequence. So this is linear time, at least. It's not very smart. And in fact, people had been using this for a while, and there was a fundamental statistical flaw in the statistic, which caused, I think, incorrect inferences to be made. And this is, I believe, my only real formula. So we just had this XW times YW for D2. But all statisticians know, and all elementary students in statistics know, subtract the mean, divide by the standard deviation, yeah? So if you subtract the mean in each of these cases and do a centered term, then you can write D2 as the sum of the centered term plus some other things. And this representation kind of shows you what's going on. When the letter distribution is uniform, the second terms, the PW, YW, PW, XW, those are constants because there's a constant number of k-letter words. So when the letter distribution is not uniform, then the second and third terms have statistical variation. So there's a completely different variance even for these two cases. And the second and third term dominate when they're not constant. And that's not very interesting because they're just about how the X sequence and how the Y sequence is behaving. So you got it. So we spent a bunch of, it's a lot of fun for an applied probabilist to mess around with this. Also, Larry Shepp, who passed away recently when he must have been a baby, in 1964, he had this result that Feller puts in his second volume. If X and Y are mean zero normals, X times Y divided by the square root of the sum of the squares is also normal. And so we did an analogous statistic for this. The last thing I want to say, which I won't be able to answer good questions about, is that, well, maybe I can just stick here. This stuff is very weak for statistical inference. It's just a screening tool and I think not fundamental. So what are we going to do as these sequences grow and grow and grow, and this is going to run blast down in the road. So what in the world is going to happen? And Bonnie Berger has been doing data compression, genome comparison stuff. And so this is a slide from her, and I just did one slide of, this is comparison. I don't know whether they're all the yeast, maybe one genome against an increasing number of yeast genomes. And the upper line is BLAST, and the bottom two are two different versions of her compression, which gets very good sensitivity for detecting what blast detects. So I think there's a tremendous future for her method. But you get my theme here that big data or lots of data or whatever comes along has to change what you're doing, and you just have to figure out some new methods that will cope with these huge problems. And we haven't had our panel discussion, but I'm occasionally asked about the future of bioinformatics, and I think the future of bioinformatics can be predicted exactly by the future of biotechnology, which will produce the data we have to cope with. Thanks a lot.
Thank you, Mike. We have time for questions, and there are 2 mics around, so if anyone... Could we have light, please, in the floor? It would be better. אפשר להדליק את האור בעולם? So, if anyone has a question, please come to the mic.
I have a question. How do you think much longer reads will impact all the stuff you talked about?
Yeah, that's a good question, and I don't really have a good answer. But I mean, you know, some of these methods, like where people, I think of his name, people who were taking the reads and trying to get sort of special keywords out of them to compress the data, I think will really be helpful. It depends on the quality of these really long reads, of course, but I think that's maybe that's our only hope.
Thank you.
So one question that I have, you mentioned that the Lander-Waterman model for mapping is not useful for the deep sequencing data. So why is that?
So it would be useful if you had good uniform libraries. It's the non-uniformity of the library that you're sampling from that can really screw you up.
Any other questions? So one more question I would like to ask: if so, you know, if the data keeps piling up and at an increasing speed, you know, maybe even scanning the whole data just to, you know, no matter what algorithm you have for comparison, would become the bottleneck. So, you see any way around this?
I certainly don't, but I have a lot of faith in the ability of humans to eventually cope with this, but I certainly don't know myself.
Yes.
So Mike, these compression algorithms, they are only basically a linear decrease, aren't they? They are really solving the exponential growth problem? I mean, when you're trying to use your keywords, is it a linear decrease in time, or is it an exponential decrease in time?
You mean the Bonnie-Berger?
Yeah, and your approach.
Yeah, that I think I tried to advertise it. I'm not really qualified to answer that question.
Yeah. I think it's a linear decrease, but so we just save some time. We will run into the same bottleneck later, I think.
Let's see. Let's just.
I think so.
Yeah. So she says it's sublinear. And maybe it is. I can't quite see it from that picture, but that's not really an analysis. To me. But anyway, that's her claim is it's sublinear, which is really pretty cool.
That would be cool, yeah.
So it's worth looking at her papers, which clearly I haven't done carefully.